everyone. Today I'll be presenting a paper survey on stealing part of production language model, which was published at ICML 2024. This paper represents groundbreaking work in the security of machine learning systems, particularly focusing on practical attacks against production-scale language models. This presentation is for the course CSIE 5436 Security and Privacy Machine Learning taught by Professor Shen Chen. Here what we'll cover today. First, we'll provide a background on production language models and the motivation for this research. Sorry. Then we'll dive into the problem formulation and threat model. The core of the presentation will cover the attack methodology, including how to recover both the hidden dimension and the complete embedding metrics. We'll then look at practical attacks on real production APIs, followed by defense strategies. Finally, we'll discuss the broader implications and future research directions. Let's start with some background. Today's state-of-the-art language model includes GPT-4 from OpenAI, Claude 2 from Anthropic, Gemini and BALM 2 from Google. These models power millions of applications, but surprisingly, we know very little about their internal workings. Specifically, the public doesn't know details about the model architecture, the size of their hidden dimensions, what training data was used, or the actual model weight. This information is kept secret for two main reasons. First, there's the competitive landscape. These models cost millions or even hundreds of millions of dollars to train, so companies want to protect their investment. Second, there are safety implications. It's generally easier to attack models when more information is available about their internals. However, while these details are secret, the models themselves are accessible through APIs. This raises an important question: how much information can an adversary actually learn about a production language model just by querying its API? This is exactly what this paper investigates. So, what are model stealing attacks? By definition, model stealing attacks aim to extract model information or functionality by querying a black box API. The field generally focuses on two main objectives. First, there's accuracy. Here, the stolen model should match the performance of the target model on some particular domain. For example, if you are attacking an image classifier, you might want your stolen model to achieve similar accuracy on ImageNet. Second, there's fidelity. This is more strict. Here, the stolen model should be functionally equivalent to the target model on all inputs. That is, for any valid input, the stolen model's output should approximate the target model's output. This paper focuses on high-fidelity attacks, as shown in this diagram. The adversary queries the black box API, receives responses, and uses these to extract information and build a stolen model. This paper makes three major contributions. First, this is the first practical extraction of precise information from production large language models. The authors successfully recovered the embedding projection layer, which is the final layer of the transformer, and confirm the hidden dimensions of several OpenAI models for the first time. Second, the attack is remarkably efficient. For the smaller models like ADA and Babbage, the complete attack cost less than $20. With GPT 3.0 Turbo, they estimate the attack would cost under $2,000. Expensive, yes, but not prohibitively for a determined adversary. Third, and I think this is very important, the authors conducted responsible disclosure. They worked directly with OpenAI and Google, proposed various defenses and mitigations, and only published after both companies had implemented protections in their APIs. Now let's look at the problem formulation. A standard language model can be represented mathematically as f theta of p equals softmax of w transpose times g theta of p. Let's break this down. Here, g theta is a function that takes an input sequence of tokens and computes hidden states. This is the main transformer network. W transpose is the embedding projection matrix. This is the target of the attack. H is the hidden dimension size. I is the vocabulary size. And here's the key insight. H is much smaller than I. Look at this diagram on the right. Input tokens flow through the transformer network G theta to produce hidden states in the H dimensions. Then the embedding projection matrix W maps from H dimension to I dimension to produce output logits. Finally, softmax converts these to probabilities. For concrete numbers in llama models, H ranges from 4,000 to 8,000, while I is 32,000. GPT-4 has a vocabulary of approximately 100,000 tokens. This difference in dimensionality, that H is much smaller than I, is the fundamental vulnerability that these attacks exploit. Let's define the threat model precisely. The adversary has query access to the model API, denoted as script O. They can specify input prompts and receive output based on the API's capabilities. Importantly, the adversary has no additional information, no side channel information like timing attacks, no knowledge of the implementation details. The paper studies three different API settings chosen for specific reasons. First, the O-Logit API is a pedagogical baseline where the API returns the complete logit vector. This doesn't exist in practice, but it helps us understand the fundamental attack. Second, the top K log probes plus logit bias API represents real APIs like those from OpenAI and Google at the time of this research. Finally, the no log probes plus logit bias setting represents potential future constrained API where providers have removed log probe access but still allow logit bias. Here is a crucial insight that sets this work apart from prior model stealing attacks. Traditional model stealing attacks work bottom-up. They start from the input layer and try to reconstruct the network layer by layer. This approach doesn't scale to large language models for several reasons. LLMs use non-ReLU activations, have attention mechanism layer normalization, residual connections, and are orders of magnitude larger than previously attacked models. This work takes a completely different approach, top-down. Instead of starting from the input, they directly target the output layer. Why does this work? Because the final layer projects from each h-dimensional hidden space to i-dimensional logit, where h is much smaller than I. This creates a low-rank structure that can be exploited. As shown in this diagram, prior work tried to go from input to hidden to output, marked in red, and this doesn't scale. This work, marked in green, goes directly to the output layer and exploits its mathematical structure. Let's look at the first step, recovering the hidden layer dimension. The core idea is beautifully simple. Even though each output logit vector is I-dimensional, potentially 100,000 dimensions, they all actually lie in an h-dimensional subspace. Why? Because they are all produced by multiplying an h-dimensional hidden state by the embedding matrix W. This algorithm is straightforward. First, we initialize n random queries, where n is larger than h. We collect the logit vectors from these queries into a matrix Q. Then we compute the singular value decomposition of Q, which gives us singular value lambda 1 through lambda m in descending order. The key step is finding the largest gap between consecutive singular values. The gap occurs exactly at the hidden dimension edge. Why does this work mathematically? Each logic vectors can be written as W times g theta of P. So the matrix so the matrix Q equals W times H, where H contains all the hidden states. Since W has H columns, and assuming the hidden states span the full H-dimensional space, Q has rank exactly H. The SVD reveals this rank by showing where the singular values drop dramatically. Let's look at the results. On the left, we see the attack applied to Pythia 1.4b, which has a hidden dimension of 2048. When we make fewer than 2048 queries, the matrix doesn't have full rank yet, so we can't identify the dimensionality. But once we cross 2048 queries, something beautiful happens. The number of significant singular values stops growing. It caps at exactly 2048, revealing the model's hidden dimension. On the right, we plot the differences between consecutive singular values in log space. There's a massive spike at the 2047th singular value, clearly indicating where the true singular values end and numerical noise begins. The table shows results across 6 different models. For 5 out of 6 models, this attack recovers the hidden dimensions almost perfectly, with an error of 0 or 1 dimension. The one exception is GPT-2. Small, which represents 757 instead of 768. Interestingly, this isn't actually a failure of the attack. The model truly has an effective dimensionality of 757, despite having 768 8 parameters, which we will discuss in the backup slides. Now, for step 2, recovering the actual embedding matrix weight. The mathematical foundation is straightforward. We have our query matrix Q equals W times H, where H contains the hidden state from our queries. When we perform SVD on Q, we get U times sigma times V transpose. Here's the key insight. We can show that U times sigma equals W times G for some H by H matrix G. This is proven in lemma 1 of the paper. So while we can recover W exactly, we can recover a transformed version of it. Why can't we get W exactly? This is guaranteed by the model's inherent symmetries. Due to residual connections in transformers, there's an H by H dimensional space of transformations that leave the model's output completely unchanged. So recovering W up to this transformation is the best we can theoretically do. How much information do we lose? For an affine transformation, we lose H-squared parameters. For an orthogonal transformation, which is a tighter bond, we lose approximately H-squared over 2 parameters. But the embedding matrix has I times H parameters total, so we are still recovering the vast majority of the information. For example, with H equals 2048 and I equals to 15,000, we recover over 99.99% of the parameters. Here are the results of full embedding matrix instruction. The table shows 6 models, their true hidden dimensions, the extracted sizes, and most importantly, the root mean square error. For GPT-2 small, we get an RMS error of 4 times 10 to the minus 4. For the Pythia and Llama models, we get errors in the range of 3 to 8 times 10 to the minus 5. These numbers might seem abstract, so here's a crucial comparison. If we compare a randomly initialized embedding matrix to true weight, we get an RMS error of about 2 times 10 to the minus 2. That means our extracted matrices are 100 to 500 times more accurate than random. This demonstrates that we are extracting real, precise information about the model's weight, not just noisy approximations. Now let's move to our practical attacks on production APIs. Before the mitigations were implemented, the OpenAI had specific constraints. Sorry, let me have a sip of water. Okay, where were we? API. Okay. It would return the top 5 log probabilities, not the full Logit vector. It allowed Logit bias for up to 300 tokens per query, and the Logit bias was restricted to the range from negative 100 to positive 100. So the challenge becomes, how do we recover the full Logit vector from just the top 5 log probabilities? The API can be formulated mathematically as shown. Given a prompt P and bias B, the API returns the top k values of the log softmax. The log softmax equals the logit plus the bias minus the log of the sum of the exponentials of all logits plus biases. This normalization constant is what makes the problem tricky. The key insight for our practical attacks is to use one token as a reference point. Here's how the method works. First, we choose a reference token R, typically the most likely token without any bias applied. Then, for each batch of our 4 tokens, let's say token I plus 1, I plus 2, and I plus 3, we apply large bias B to all 4 of them. The reference token R naturally appears in the top 5 because it's already likely. Now we observe the log probability of all 5 tokens. The beautiful thing is that the relative difference between logits can be computed as Z R minus Zi equals the difference in log probabilities minus the bias B. The normalization constraint cancels out when we take differences. This is remarkably efficient. The query cost is 1/4 of a query per logit. Because we extract 4 logit per query, the token cost is approximately 0.5 tokens per logit, accounting for both input and output tokens. We can improve this even further with a cost-optimal attack using multi-token generation. Here's the observation. If we can force the model to generate a specific sequence of tokens, we can extract logits for each generated tokens, not just the first one. The strategy is to apply a large bias B to some token X and a smaller bias B prime to 4 other tokens. Where B prime is less than B, if we set B prime large enough, these 4 tokens will still appear in the top 5. But if we set B prime small enough compared to B, the model will always choose to generate token X, so we get a sequence like X, 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 and we can extract logits at each positions. The efficiency analysis is elegant, with an expansion factor of m tokens. Our query cost becomes 1/4m per logit, and our token cost is 1 plus m over 4m. As m approaches infinity, our cost approaches 1/4 per logit, a 4-fold improvement over the basic method. Unfortunately, after responsible disclosure, OpenAI removed the ability to get log probabilities for prompt tokens, making this particular optimization unavailable. But it demonstrates the principle of how carefully designed queries can dramatically improve attack efficiency. Here are the results of attacking real production models from OpenAI. The table is divided. Sorry, I forgot to change the slide. This table is divided into dimension extraction and full attack queries. For data which has hidden dimension of 1024, confirmed correct with the checkmark, dimension extraction requires less than 2 million queries and costs approximately $1. The full attack to extract all weight requires less than 20 million queries and cost $4. For Babbage with dimension 2048, the cost was $2 for dimension extraction and $2 for the full attack. For Babbage 220002 with dimension 150 1536 dimension extraction cost $2. The full attack was not implemented to preserve security, but is estimated at $12. For GPT 3.5 Turbo, the dimension was successfully extracted, marked with a check mark, at a cost of $800. The full attack is estimated at $8,000. The actual dimension size is marked with an asterisk because per OpenAI's request, the authors agreed not to publish this specific number, though they confirmed it was correct. These are the first confirmed hidden dimension size for these closed source models. The attack costs are remarkably low compared to the value of this information. This table compares different attack methods for recovering individual Logit values. The key metrics are bits of precision and queries per Logit. The best practical attack, the reference token method with top 5 log probes, achieved 23 bits of precision with only 0.25 queries per Logit. That's excellent precision and efficiency. The linear system method, which we discussed, is theoretically more efficient. Actually achieves only 11.5 bits of precision and 0.64 queries per Logit due to numerical stability issues. For more restricted API, the binary Logit bias attack achieved 6.1 bits of precision at 1 query per Logit. Now the most interesting part is the log prop free attacks, marked with an X in the log props columns. Even without any log prop access, the best attack achieves 18 bits of precision at 3.7 queries per Logit. The theoretical lower bound for this setting is approximately 1.5 to 3.5 queries per Logit, so this attack is remarkably close to optimal. This demonstrates that even very restricted APIs can still leak substantial information about the model's internal parameters. Now let's discuss defenses. First, prevention strategies that completely break the attack. The simplest defense is to remove Logit bias entirely from the API. However, this has a major downside. It breaks legitimate use cases like constraint generation, control text generation, and various research applications. So while effective, it's not very practical. A better option is to replace Logit bias with a block list. Instead of allowing arbitrary bias values, just let users specify which tokens the model is prohibited from generating. This supports some of the same functionality but prevents the attack. The cons is that it doesn't support all use cases that Logit bias enabled. Architectural changes are another option. We could modify the model's architecture to insert an intermediate layer going from H dimension to T dimension, then T to I dimensions. Where T is greater than I, we would add a nonlinearity between these layers. This breaks the low-rank structure that the attack exploits. However, the cons is that this is computationally expensive. The final layer is already large and quadratic in vocabulary size. Finally, there's post-hoc dimension spoofing. After training, we can artificially expand the dimensionality of W by concatenating orthogonal vectors with small singular values. During inference, we concatenate random Gaussian noise to the hidden state. This misleads the attackers about the true model size, making them think the model is wider than it actually is. Mitigation don't completely prevent the attack but make it more expensive or difficult. First, we can implement Logit bias XOR log props. Don't allow both in the same query. This forces the attacker to use less efficient method and makes the attack approximately 10 times more expensive. Second, add noise to the output. This reduces the precision of extraction and creates a trade-off between security and utility. Too much noise makes the model less useful. Too little doesn't provide adequate protection. Third, rate limiting. We could limit the number of Logit bias queries allowed per prompt. The issues here are substantial though. It's hard to set the threshold without revealing information you need to maintain state across all user queries, which raises privacy concerns. And users can easily create multiple accounts to bypass the limits. Finally, anomaly detection. We could implement systems to detect suspicious query patterns similar to adversarial example detection system. The challenge is that these detection systems are often themselves vulnerable to adversarial attack, as shown in recent research, so many mitigation here would need to improve on the current state of the art to be truly robust. Let me show what actually happened after responsible disclosure. Both OpenAI and Google implemented mitigation to prevent or slow down these attacks. Both companies worked directly with the authors before publication to develop and deploy appropriate defenses. The graphs shown two defense strategies. On the left is the noise defense. As we add more noise to the logit, the root mean square error in the extracted embedding increases. This demonstrates the security utility trade-off. More noise means better security but worse model performance. On the right is dimension spoofing applied to GPT-2 Small. The left panel shows the true model with 768 dimensions. The right panel shows the same model after post hoc modification to appear as if it has 1024 dimensions. This successfully misleads the attacker into thinking the model is wider than it actually is. These aren't perfect defenses. They make the attack more difficult or expensive rather than impossible, but they raise the bar significantly for potential attackers. Let's discuss limitation and future research directions. Currently, the attack only extracts one layer, the final projection layer. Recovery is only up to an edge-by-edge transformation, not the exact weight, and the attack requires specific API features that may not always be available. Future work could explore several exciting directions. First, breaking symmetry with quantization. Since production models use 4-bit or 8-bit quantization, the weight takes discrete value. In principle, this could allow recovery of the exact metrics, since only one of these infinite possible transformation would have properly discretized values. However, this is an NP-hard problem in general, though it might be tractable for specific instances. Second, extending beyond a single layer, can we somehow deal with the nonlinearities and extract deeper layers? There is no obvious approach currently, but this would be a major breakthrough. Third, removing the logic bias assumption entirely. Can we use all the API parameters like temperature or top K to leak logic information? In the long run, completely hiding logic information might be challenging due to both user demand for features and the ability for clever adversaries to infer information through indirect means. This work has significant implications for both machine learning security and research and industry. For machine learning and security research, this is the first practical extraction of production LLM components. It demonstrates that model stealing is not just a theoretical concern, it can be applied to the largest, most sophisticated models deployed today. This motivates the field to focus more on practical attacks against real systems rather than just studying toy examples. For industry, the key lesson is that small design decision can have major security implications. Who would have thought that these seemingly innocuous logic bias feature could enable weight extraction? This shows the need to consider adversarial perspectives when designing APIs, and to carefully balance functionality against security. There are also implications for responsible scaling policies. Many AI safety frameworks require hardening security such that non-state attackers are unlikely to steal model weight, but the focus is often on traditional security, patching software, maintaining physical server security, performing regular audits. This work shows we also need to consider mathematical and cryptanalytic attacks. The API design itself can be a vulnerability regardless of how good your traditional security is. Let me summarize the key takeaways from this paper. First, practical model stealing is possible and has been demonstrated. The authors extracted parts of the GPT 4.5 ADA in Babbage for $4,000 to $8,000. This provided the first confirmation of hidden dimension for these closed source models. Second, the top-down approach exploits the low-rank structure of the final layer. Because H is much less than I, SVD can reveal the hidden dimension, and we can recover W up to unavoidable symmetries in the model architecture. Third, defenses exist but involve trade-off. We must balance removing features against maintaining utilities, adding noise against preserving model qualities, and implementing detection system against false positives. Finally, significant open questions remain. Can we extract more than one layer? What about alternative API designs? How do we properly balance security and functionality? These questions will drive future research in this area. Here are the key references for this work. The main paper is Collini and colleagues ICML 2024 paper. Important prior works include Trauma and colleagues 2016 security paper that introduced model stealing attacks, and 2020 work on high fidelity extraction. The technical report for GPT-4, BALM, and Llama provides context about modern language model and their architectures. Just for the brevity of the video, I will skip the details of about the mathematical details and also some normalization layer impact and whatsoever. Okay, let's also back up slides. So that's it. So thank you for your attention. I hope this presentation has given you insights into both technical details of this attack and its broader implication for machine learning security. This paper represents an important milestone in demonstrating the model's scaling as not just in theoretical concern but a practical threat to production system. And happy to take any question you might have about the tech methodology, the defenses, the ethical consideration, or the broader implication for machine learning security. Again, if you have any question, please leave a comment below. This paper is still in part of production language model by Collini and her colleagues, published at ICML 2024. Again, this presentation was for CSIE 5436 Security and Privacy Machine Learning, taught by Professor Shen Chen. Thank you.